Concrete is a material defined by a massive mechanical imbalance. It possesses immense compressive strength, easily bearing the weight of skyscrapers. But under tensile stress, it shatters without warning, the moment flexural loads pull it apart. Introducing steel reinforcement solves this tensile deficit. The steel bridges the microscopic fractures, locking the concrete together and stabilizing the structural member. This marriage of materials requires strict volumetric control. Embed too little steel, and the member remains vulnerable to failure. Embed too much, and the structure faces equally fatal construction flaws. The Indian Standard Code, IS 456-2000, governs these boundaries, dictating the precise minimum and maximum reinforcement percentages for every structural element. While students often memorize these percentages for exams, each value encodes a precise structural response to a specific failure mode. We are going to derive the exact steel requirements for footings, slabs, beams, and columns from the ground up, relying purely on physical mechanics. These code limits exist at the exact thresholds where thermal mechanics, flexural yielding, and concrete rheology demand them. Starting at the foundation, footings and flat slabs share a distinct geometric trait: a massive, expansive surface area relative to their shallow depth. This geometry makes these members vulnerable to volumetric reduction, driven by temperature variations and rapid moisture evaporation, well before they ever face a structural load. This phenomenon, drying shrinkage, induces severe internal tensile stresses that attempt to tear the slab apart from within. IS 456 mandates a baseline minimum steel percentage in these expansive members, specifically to intercept and arrest these thermal and shrinkage cracks. The code sets this minimum at 0.12% of the gross cross-sectional area when using high-yield strength deformed bars. For mild steel, the requirement increases to 0.15% to compensate for its lower yield threshold. While slabs are theoretically capped at a 4% maximum, their massive cross-sections mean they are generally lightly reinforced, and this upper limit is rarely approached in practice. In footings and slabs, minimum reinforcement provides an environmental shield, preventing the concrete from tearing itself apart. In structural beams, the primary threat profile shifts from environmental shrinkage to pure flexural tension. An under-reinforced beam is a liability. If the concrete cracks before the steel yields, the beam fails suddenly and violently, without warning. Clause 26.5.1.1 mandates a formula so steel yields before concrete crushes. It balances required steel area against beam breadth and effective depth, inversely proportional to steel yield strength. Higher yield strength drops the required percentage. Fe 415 needs 0.20%, and Fe 500 requires roughly 0.17%. Beams are capped at a 4% maximum steel density. Exceeding this limit crowds the bars, destroying the vital bond strength required for the concrete and steel to act as a single unit. These minimums force the structure to bend and deform under extreme stress, providing a visible, life-saving warning before total failure. Columns, the most critical members of the structure, demand an absolute, non-negotiable minimum of 0.8% steel. This requirement seems high for a vertical member subjected primarily to downward compression, nearly 7 times the baseline steel of a horizontal slab. However, perfect axial loading is a mathematical myth. Physical columns always encounter accidental eccentricities, slight misalignments that induce bending moments. The 0.8% minimum protects against these indisible moments, mitigates long-term material creep, and prevents lateral buckling under massive loads. While the 0.8% minimum is strictly enforced, IS 456 allows for a theoretical maximum steel volume of 6%. Site reality often overrides this theoretical limit, leading experienced structural engineers to cap column designs at 4%. This unwritten rule is driven by the lapping zone, the critical area where 2 vertical rebar cages must overlap to extend the column's height. A column designed at a 6% steel ratio will double to a 12% density within this overlapping splice zone. This conflicts with concrete rheology, the flow of wet matter. An overlapping 12% steel grid acts like a literal sieve, catching aggregate and blocking fluid cement. The result is honeycombing, internal voids that render the theoretical strength of the steel useless. The 4% practical cap tethers the theoretical physics of the design office to the physical rheology of wet materials on the construction site. Applying these code limits correctly requires dismantling a pervasive calculation error common among students and novice site engineers. Every percentage mentioned, from 0.12% in slabs to 4% in columns, applies strictly to the gross cross-sectional area of the member. A fatal error involves taking this geometric area percentage and multiplying it by the physical mass density of steel, 7,850 kilograms per cubic meter. This calculation conflates a geometric ratio required for structural integrity with the mass estimation used for purchasing materials. This blueprint maps the core requirements of IS 456. It shows the 0.12 and 0.15% minimums for slabs, the yield strength formula for beams, and the 0.8% structural floor for columns, all capped by a practical site maximum of 4%. These limits manage foundation temperature expansion, guarantee flexural yielding in beams, and provide buckling resistance in columns. Mastering these precise thresholds allows engineers to design structures that withstand the brutal physical realities of the field.